Hi Carter, hi Kat. Could you just let me know if you can hear me all right? Okay, perfect. All right, good morning, everyone. For those who are joining in, we'll give a couple of minutes before we start just to make sure whoever needs to be here is here. So yeah, take your time to settle in. All right, perfect. Thanks for those of you joining in. We'll just wait 1 or 2 more minutes just in case everybody is joining in to get started. All right, perfect. I think we have some critical mass here. So before I begin, just want to make sure all of you can hear me all right. Could you just give me a thumbs up on the reaction or maybe just write on chat? That sounds good, that you can hear me all right. All right, perfect. That sounds great. So yeah, good morning, everyone, and thank you again for being accommodating. We'll have few of these lectures via Zoom, but they will all be recorded, posted on the YouTube link. And so we can begin for today. I will also, by the way, give breaks as usual. So hopefully this is not like this Zoom meeting won't be like, also too burdensome. So all right, so we'll start lecture 10, some quick announcements. As you know, your exam is day after tomorrow, and it will be in the room A115. So just make sure to be there a few minutes early. We'll start the exam sharp on 8:30 a.m. Then you'll have 90 minutes to write the exam until 10 a.m. And then for 10 minutes, you will have time to upload your exam one on Gradescope essentially, which is where we will grade the exam. As I've said before, but just to remind you, exam is open book notes, internet, so you don't have to memorize anything. You will have access to everything. The only thing we request, and please make sure you know you do honor it, is that you are not checking emails or doing any messaging or so on during the exam. We just you're all PhD students, and so you understand that you kind of just respect that policy. So today I will be covering material for exam one, as well, like a review and then some Q&A time. But if not, you will also have more opportunity to do that. Uh, what's the policy on using AI? Yeah, I mean, you're welcome to use. I'm not sure if it's going to be too helpful, but if you want to use, or if it sort of helps you, you can try to chat with an AI bot if during the exam. Uh, I don't think it is going to be too useful. Probably the most useful place for this course in using AI would be to like help you code and stuff like that. And you're welcome to use that if that helps you during homeworks. During exams, I don't particularly see any place, but if you find a creative way to use AI, let me know. I'll make a note of it myself. But yeah, so you are welcome to use it. We will not be policing it. But we do request if you do use it, maybe just let us know. We'll not deduct any points. This is just so that, as things are evolving with, all of these, bots and sort of large language models, it'll be useful for us to know, what it can do that, maybe help you during the exam or something like that. So if you can share that with us, let us know, but you are welcome to use it if you would like. Uh, any other questions for the exam, by the way, for like the policy? You can put in chat or also unmute yourself and ask. Okay, seems like all good. But yeah, so Sauradeep will have office hours tomorrow from 4:30 to 6 p.m. in B322. Hopefully, I got the room number correct. But Sauradeep will also send a Canvas announcement just to remind you for tomorrow. And then all the materials have been posted. So thanks to several of you who pointed out some of the small errors there were in, like some of the lectures are not updated and so on. So all lecture notes should be up to date. I'll make sure that today's lecture is also up to date. Then you have all the videos. The couple of videos that you did not have recorded, the first week of February videos, you also have access to the Spring 2024 one. So if you would like to see that. And then practice exam solutions, homework solutions are all uploaded, and also supplementary videos are there. I believe there is also maybe like a review for exam one, which you're welcome to check out. I think it's probably useful for you to check. And I'll upload today's video after the lecture as well. So any questions on the exam? Anything that comes to mind that has not been addressed? I'll just give a minute. If there are any questions, feel free to put on chat, raise your hand, or unmute yourself and just ask. Okay, so it looks like things are okay. If questions also come up, feel free to put in chat, and I'll try to monitor it as I go along. But yeah, so that's great. Basically for today, the agenda is very simple. In the first part, before the first break, what I would like to do is I'd like to give you a brief, just like discussion on FFT or the finite Fourier transform. This is the topic we started last time. We did a few examples. So I'll just discuss one more example. And by the way, this came up after discussing with some of the students over email about different methods in FFT. I think it's useful to do this in the class, and I'll also show you a Python code to kind of discuss a more advanced problem. You certainly won't be expected to solve something this complicated in your exam, but this is just for you to kind of get a taste of something advanced, and hopefully also clarify some of the concepts of FFT. Then we'll take a break. Then I'll do a 30-minute sort of review and so on. And then we'll take another break. And then whatever time is remaining would be for Q&A. I also am happy to sort of answer any questions that you have via email. I might be a little slower just because of travel. I'll respond, but I do generally respond to everyone who has probably reached out to me. So I'll also make sure to be available on email as you're approaching exam. Okay. Any questions or clarifications needed before I begin the recap and stuff? All right, perfect. All right, so let's keep going. So last time we discussed FFT. So we have discussed several kinds of problems. So we have discussed 1D steady problems, approximately 1D steady problems, including, a pseudo steady state from or 2D to 1D problems. Then we have also discussed semi-infinite geometries or Rayleigh times where we use similarity transforms and perturbation methods. And we'll discuss some of that in the review as well. But the real focus last lecture was on FFT, which is for linear problems. So again, remember linear problems are the one where you don't have any the dependent variable being multiplied in itself. So it should be something like del theta by del tau, del square theta by del x square. I cannot have any term like theta del theta by del x or theta to the power of 1.5. So it has to be a linear problem for us to use FFT. And you also need to have boundary surfaces like x is equal to 0, x is equal to L. Now, FFT is also available in Cartesian in cylindrical and spherical coordinates. For this course, we will not discuss the cylindrical and spherical coordinates, but that is available in the book. If you get sort of, if you find a problem where you have to use in switch coordinates, just be aware that this method is also available for you to use in different coordinate system. All right. So what's the basic idea of FFT? So the basic idea of FFT is that we will propose a series solution. So all we need is a linear system and boundary surfaces. We'll propose a series solution where we'll have two terms, where we'll have theta n of tau and then phi n of x. So we'll choose x because x had the boundary conditions should be in this variable. In this case, it is written in terms of x. Based on the boundary conditions, these boundary conditions help you define the second step, which is the find the basis function. And to find the basis function, you basically look up in the table. And so you have already done this in your homework problem as well, that if you don't find the exact system that is available for you in the table, you use the closest one. So if the values are constant but not 0, you will use case 1. If one of the derivative is, derivative and value, one boundary condition is about a value and the other is about a derivative, you will use case 2 and 3. If both are derivatives, then case 4, like in the table. But if it's 0, that's the most ideal case. If it's non-zero, you do have some sort of issues when you sort of start doing the problem. It can create convergence issues and so on, but you can still choose that same basis function. Okay, and that's perfectly reasonable, and you can just use it, and no points will be detected for that. Or like in general, even if a problem, you will be able to solve it even if you're not able to find a clever way of reducing the boundary conditions and make them homogeneous. Next, once we have the basis function, then we modify the governing equation using the simple modification is that we multiply it with phi and dx, take the integral over the limits of x, and then we change the initial condition, and then finally we solve and substitute. So that's sort of the 5 steps. So before I begin and discussing some of the example problems we discussed last time, any questions on any of these steps that might have come up while doing the homework? Or lack of, if there is any lack of clarity in any of these steps? All good? Okay, so let's keep going. So the last time what we discussed was this same setup. We are just changing the boundary conditions and initial conditions. So these were 1D unsteady problems. So it was X. So these were 1D unsteady problems. By the way, as you might have seen, I have not made this restriction of 2D unsteady, 3D unsteady. Technically, you can solve actually all of them using FFT. You can have 2D unsteady problems and so on. You can also solve them using FFT, just that we will not be doing such an advanced problem in this course. But if you look in the book, it actually does discuss some of these strategies for more complex problems, just so that you are aware. So it's a pretty general technique that way. All right, so for 1D unsteady problems, basically what we focused on in the class was initially if you have something that is, C is equal to C naught, then and the boundaries are 0. So we discussed how the concentration was like this, then slowly becomes, diffuse, starts to diffuse out like this, goes inside, and then slowly, it decreases and becomes steady state like this. So this was the concentration profile we discussed. We plotted this using the FFT. We also discussed the early time solutions, how you can sum two error functions and so on. That also gives you this. So this is the problem we solved. This was a very simple one because we could use case one very simply in this problem and just use that to do this. All right. The second problem was slightly different, is that in this case, initially we did not have any CA, but we had C naught on the left hand side and a derivative on the right hand side to be 0. So in this case, initially, essentially the concentration profile is just 0 like this. Then slowly the concentration starts to diffuse in, keeps diffusing in, and then as it reaches the last step, it basically hits the wall, then it has to start going up the wall because the gradient has to be 0. And finally, the steady state is equal to equal to 1 essentially. And that's or C is equal to C naught or theta is equal to 1. And this is also the problem we discussed last time in detail. You can again superpose a complementary error function, and we showed how it was able to match well until it hits the boundary. When the boundary effects start to come in, you basically start to see deviation with FFT. So that is the second problem we did in the class. Then we did not really do this problem in detail, but we discussed also the problem of same problem, CA x comma 0 is equal to 0 is if you also have a reaction going on. In that case, essentially, it will be a similar setup, but we also have to remember that our final boundary condition may not necessarily look, but final concentration profile will not look like the one of C is equal to C naught. So basically, initially, it will be like this. You'll keep on going like this. And then depending on the Damn-Kohler number, your final boundary condition, final equation might look like this. So this steady state profile, let me just write the full thing. Steady state profile will be dictated by profile dictated by Damn-Kohler number. Okay. So that's sort of the idea, is that at the end, even if the unsteady term is 0, you can also have reaction and diffusion balancing each other out. But if there is no reaction, I need to make sure that there is no flux, because my right hand side does not have any flux, or right hand side boundary does not have any flux. So I have to make sure that there are no concentration gradients. But if there are reactions, I can expect some concentration gradients and so on. And by the way, for these two problems, we also discussed that we will define theta as C by C naught. However, instead of proposing a series for theta, we'll propose series for theta minus 1, because this allows us to homogenize the boundary condition. Because I have one of the boundaries as C is equal to C naught. So if I subtract 1 from after non-dimensional length in C naught, I can basically make it 0, and the derivative does not really is impacted by that. And so finally, basically, I can essentially then propose something like phi n of x tilde. For this is how the approach is. And so we haven't really totally discussed this in detail. All I'm just sort of showing you is this is the kind of system that we can expect, and you can also solve yourself if you need to. Okay. So any questions on these different sort of cases that we have discussed till now for the concentration problem? Any clarity on the profiles? Anything that's confusing? All right, so I'm assuming you're all following this, and so this is all good. So, all right, so what's the next thing that I really want to focus on today is actually discuss a case where essentially we have to focus on a problem where we don't have a profile which I can simply subtract like this and then make it go to a homogeneous boundary condition. And I will do a slightly more complex problem. There is one done in a supplementary video, which you are welcome to take a look at. It's actually a long video, but I'll do even a slightly more complex problem and also do Python coding to sort of show you what the approach is. And so what this problem is is same setup we have been discussing, but a slightly different boundary condition. So we'll say CA of x comma 0 is equal to 0, CA is equal to C naught, CA is equal to 0 on this side. So the right hand side has the boundary condition of C is equal to 0, and I have A going to B using a volumetric reaction and first order reaction. And first order reaction. X is equal to 0, X is equal to L. Okay. So sort of that is the goal that we have for this problem. So now the goal is we have to find CA of x comma t. This is what we want to find as usual. All right. So now the first thing first here is that I'll do this a little bit quickly because we have done this a few times now. Is that you can write the governing equations. Governing equations. So governing equation is del C by del T plus V dot del CA is equal to dA del square CA plus RA. This will go away. And so we'll get del CA by del T is equal to dA del square CA by del x square minus KVCA. Okay. So hopefully that's not too bad. KVCA with the negative because we are consuming CA. The first order reaction and only diffusion is within the x direction and del CA by del T. Then initial condition and boundary condition. Initial condition is CA of x comma 0 is equal to 0. That's pretty straightforward. And boundary condition are also very easy. That we are given the value simply SC naught and CA of L comma T equal to 0. All right. And then we also have, we'll non-dimensionalize this. And we'll get del theta by del tau is equal to del square theta by del x tilde square minus damn color theta. And then we'll say theta of x tilde comma 0 is equal to 0, theta of 0 comma tau is equal to 1, theta of 1 comma tau is equal to 0, and tau is equal to dt by L square, x tilde is equal to x by L, naturally theta is CA by C naught, and then damn Coulomb number is equal to KV L square by dA. Okay, so take your time. Let me know if there are any questions, but this is the problem basically which we want to solve. Okay. Any questions or clarity needed for anyone? All right. So hopefully this is clear and you're all following along with this idea. And so the what's the challenge? So obviously this is a linear problem, and that we have a boundary surfaces. So we can use FFT. So we can use FFT. Now the issue in this problem is that like I cannot just simply subtract like a theta bar as theta. There is a comment here. What's the d in the numerator of tau? Oh, sorry. Thank you. This is actually dA. Thank you for pointing out, Summer. It's actually dA. Thank you. It's not d. It's dA. dAt by L square. So it's a diffusivity of A. Thank you. So the challenge here is that if I simply say theta bar is theta minus 1 to homogenize the right-hand side boundary condition, I end up making the left-hand side inhomogeneous, right? So that's sort of the challenge here in this problem is that uh, you are essentially sort of a simple subtraction cannot help you simply get the boundary conditions that we desire. We want to get the boundary conditions of something like both sides to be 0, so that we can use case one of our of the FFT table, but we don't have that luxury right now because we essentially have this sort of problem where we can see that the values are different. Now, on top of that, there is also a reaction going on in the system, so that also further complicates it. So let's try to first physically think through the concentration profiles, and let's, for the sake of it, let's imagine Damkohler number is high. Damkohler number is, let's say, something like 100 or something like that. So if Damkohler number is about 100 in the system, then you can imagine that if I have initial profile like this 1, 0 right here, and then I'll start to go inside, but my steady state would look something like this, right? This would be my steady state. Because if Damkohler number is so high, if you remember, I will not be reaching to the end of the pore. I'll not be reaching the end of the whole region because I will basically consume everything in the initial part of the pore, and then basically the rest of the flap profile will just stay to 0, because that's basically my reaction and diffusion balance at steady state. And so the thing to note is, and so this is Damkohler number, let's say 100, but if Damkohler number is exactly 0 or very small, then what do I expect? Then I expect slowly, so something like this. If Damkohler number is 0, again, I'll go like this. I'll start to go towards the end, but then my steady state should be simply linear, right? So the linear profile, because I know if my steady state is simply, if there is no reaction, my diffusion has to be constant, and I don't have the flux to be 0. I just have the values to be 1 and 0, which means the flux will be constant, and I'll simply get a linear profile. So my steady state profile clearly will be different and depending on the Damkohler number. However, I can see that if I have a steady state profile, it can help me satisfy my boundary conditions at least. So a steady state profile can clearly satisfy my boundary condition. And if I subtract, because it's a linear problem, remember the linear superposition principle. So if I have a linear problem and if I subtract the steady state solution from it, or rather, from the actual solution, or I sort of propose that I'll find two solutions, one the unsteady part and one the steady part, then the steady part can take care of the boundary conditions. So now let's try to do what I'm trying to say here in words. I can say theta of x tilde comma tau is theta of steady state x tilde. Okay, theta of steady state x tilde, and then something that is remaining part is theta bar of x comma tilde. Okay, and why am I allowed to do this is that I will force, basically I'll force that this is my solution, and as long as both of these solutions are satisfying my governing equations and boundary conditions, self-consistently, I'm allowed to do that. So let me see if there's a comment. What is steady state linear when Damkohler number is 0? It's theta versus x. So linear summer is the theta versus x. So we are plotting all this concentration versus x tilde, theta versus x tilde. So when it's steady state, essentially I'll get a linear profile of concentration, or in this case, I'm just writing a dimensionless concentration as theta. So that will be linear. Okay. Any other questions? Okay, so now let's keep going. So now what I will do is I will basically say I'll substitute this in my governing equations and boundary conditions. So substitute this in governing equation and boundary conditions. Okay. And follow along because a lot of books don't actually show you these steps. So I have found this to be very instructive to do this on my own. So what I can do is I can say del theta by del tau is equal to del square theta by del x tilde square is equal to minus Dam Coulers times theta. Now I can also say del of theta steady state plus theta bar by del tau. It is equal to del square theta steady state plus theta bar by del x square minus Dam Couler theta steady state plus theta bar. Okay, so I've simply just substituted theta as theta steady state plus theta bar. Now I do know that because it's a steady state solution, I can simply say this term goes to 0 because it's not dependent on time. It is literally steady state. And then I can also say that del theta bar by del tau minus del square theta bar by del x tilde square minus m square by theta bar plus is equal to del square theta, or rather d square theta by dx tilde square So hopefully everybody would agree with this statement. All I have done is I've literally just allowed it to, and there's a plus here rather than minus. I've literally just taken the equation and I have just rearranged it in this form on the left and right. Does it make sense? Any questions? Any questions here? Okay, so let's keep going. So now left-hand side, I assume you will all agree, left-hand side is a function of space and time. And the right-hand side is a function of x only. Right? I mean, it is literally steady state. So right-hand side is a function of x, and the left-hand side is a function of x and tau. So how can I equate something which is a function of x and tau to a function of x tilde? Any ideas? So how do I make this how do I make this to be true? Like this is my statement. Obviously, a function of x and tau becoming equal to a function of x doesn't make sense. But how can I force this to be true if I want my superposition to work? Anybody has ideas? See, evaluate at tau equal to 0. That's a possibility, but remember then that will not be true for all times. So good thought, Joe. You're suggesting that evaluate at tau equal to 0 for the theta bar. That's a good thought, but again, so we want this to be true for all x and all times, right? We don't want to restrict it at just tau equal to 0, which okay, so that's good. Almost there. Very good. All perfect. So all of you are kind of getting there. So either the LHS has no dependence on tau or tau is independent of x, or both sides are equal to a constant. So the last parts, right? So we want it to be equal to constant, and simply we can just put them to be 0. So essentially all we are saying is that they have to be 0 simultaneously and separately. And if I do force that, my governing equation will always be satisfied. It is true that you can also put them to be a constant, but however, setting that constant is more sort of work for us. So we can simply say that they are equal to 0. That's as simple as that. And if you force that to be 0 separately, then you make sure that you sort of this superposition works, because if you plug this back into your equation, you get the original equation. And more importantly, this also physically makes sense. If you look at the left-hand side now, or the left equation right now, that looks like an unsteady diffusion equation, and the right-hand side looks like a steady diffusion equation. So basically, we have broken down theta into two parts. One, an unsteady part, which is the theta bar part, and one is steady part, which is the theta SS part. Okay, so that's sort of the idea. And by the way, this is an advanced concept. I should note that don't worry if this sort of all of the steps, such a complicated set of steps are not going to be expected for you to do in an exam. But I just want to highlight this is not sort of an arbitrary choice. We are making this through a lot of logical steps. The whole reason to do this is because we could not simplify our equations to get homogeneous boundary condition. And then it made sense that we can help use theta steady state and unsteady state to maybe help with boundary conditions. So we are not there yet. So let's keep going. And I think hopefully this will make sense. So now we have our boundary conditions, which were basically the whole point we were doing this. So we are saying theta of 0 comma tau is equal to 1 and theta of 1 comma tau is equal to 0. So that's my boundary condition. Now this implies that theta bar of 0 comma tau plus theta steady state of 0 is equal to 1 and theta bar of 1 comma tau plus theta steady state of 1 is equal to 0. Right? Again, if I want my superposition to work, this is what I want. Now, the whole point of doing this exercise is because we want to make sure, so we want theta bar of 0 comma tau is equal to 0 and theta bar of 1 comma tau is equal to 0 because this homogenizes an unsteady problem. So we choose this, and that automatically implies theta steady state of 0 is equal to 1 and theta steady state of 1 is equal to 0, which that's why we get this as the solution. Right? So basically we have satisfied now our boundary conditions because if I choose theta bar to have 0 and 0 on both ends, then automatically my theta steady state and theta steady state at 0 will be 1 and theta steady state at 1 will be 0. So hopefully this makes sense. If there are confusion, let me know and I can try to answer if there are any questions here. Any clarity needed? We'll also keep monitoring chat. All right, so hopefully we are making this makes sense to everyone. All right, so let's keep going further. So now what you can do is you can actually already solve for theta steady state because you have the boundary conditions and you have the equation. You don't need an initial condition. So I will just do it at home. It's not that difficult. It's pretty easy actually. Do it at home. But what you'll find is theta of steady state of x tilde is equal to sinh of square root of dA into 1 minus x tilde by sinh of square root of dA. Okay, so that's what you'll get out. You can quickly check this satisfies our governing equation. Our governing equation also it obviously satisfies because if you differentiate twice, you'll get a Damkohler number out. And so that's your governing equation is satisfied because you're differentiating with respect to x twice. Sinh will become cosh will become sinh again. And then, but the factor of Damkohler number will come out. And you're satisfying your boundary condition. If you put x tilde equal to 0, it's sinh square root of Damkohler number by sinh square root of Damkohler number, which is 1. And if you put x tilde equal to 1, it is sinh of 0 in the numerator, which is also 0. So this is not difficult. You can try to do this at home if you haven't, just for practice if you would like. But you will get sinh of square root of d into 1 minus x tilde, the sinh of square root of dA. Okay, so hopefully this makes sense and this is logical. Then initial condition essentially, initial condition is now theta of, we know x tilde comma 0 is equal to 0, which implies that theta bar for 0 comma time plus theta steady state. Sorry, I apologize, not 0 comma time, x tilde comma 0 plus theta steady state is equal to 0, which implies that theta bar of x comma 0 tilde comma 0 is equal to minus theta steady state is equal to minus sinh square root of dA into 1 minus x tilde by sinh of square root of dA. Okay. Any questions here? Anyone? Sorry. Sorry, apologies. Any questions? Yes, I see a question. Uh, how do you know it was a cinch instead of a sign? So the cinch was because I have a positive number here. If it was a negative, if it was a d square theta ss by d square theta ss by dx square is equal to plus dA into theta ss, then I would have a sign. But because I have the minus dA, so if something is a on the, if you take things to the right hand side and it's a positive number, then it's a cinch. If it's a negative number, it's a sign. By the way, you don't have to memorize this. This is present in Appendix B of your book, if that's something that you get confused by. How do you take its 1 minus x tilde inside cinch rather than 1 plus x tilde? So the good code question. So Summer's question is, how do you know it's 1 minus x tilde? By the way, I've taken out some steps, obviously, but you can remember if it's 1 plus x tilde, then if I put the value as x tilde equal to 1, then I will get cinch of square root of dA into 2 by cinch of square root of dA, which is not equal to 0. But when you solve the problem actually using the usual summation of sinh and cosh, you don't get this neat form. You can actually, you have to combine the terms like we did in one of the lectures earlier for a cosh problem, if you might remember, like a cosh b plus sinh b like expansion. So the 1 minus x tilde comes because of rearranging of that. Again, you don't have to worry about this part here right now. This takes some work, but you can do it at home and kind of verify that you get this result. And but yeah, we do know it's a cinch because we have the right hand side as a positive number. If it's a negative number, then it's a sign. And the 1 minus x tilde comes out because I've skipped like a few steps, obviously, that you need to do to arrive at this number. And then those steps lead to this 1 minus x tilde. Any other questions? All right, so I hope this sort of makes sense to everyone. Now I'll quickly say one last thing and then I'll not take too much time to do this because it's more repetitive, but I hope you can sort of see the form now. So now I have del theta by del tau is equal to del square theta by del x tilde square is minus dA theta bar, right? This is my equation now. I know theta bar of 0 comma tau is equal to 0. Theta bar of 1 comma tau is equal to 0. And I also know theta bar of 0 comma x tilde comma 0 is equal to minus sinh square root of dA into 1 minus x tilde by sinh square root of dA. Okay, or you can also call it minus theta SS if instead of carrying around this whole thing. What do you mean when you say the right hand side is positive and explaining when you choose? Yeah, so Samar, thanks for the question. Let me just go back to that question. So what I'm trying to say here is if this was d square theta SS by d tilde square is Damkohler theta SS. So this implies this is the positive number, Damkohler number cannot be negative. So this means it's a cinch. If it was d square theta SS by d tilde square is equal to minus Damkohler number theta SS. So this coefficient of theta SS was a negative number, then it would be a sign. So that right hand side, when you take the coefficient next to your variable, that dictates whether it's sine and cosine or sinh and cosh. So hopefully that answers the question. All right, so let's keep going here. So this is basically our problem now. So if you remember, this is very identical to the problem we have been doing before. So now we can propose a series theta bar is equal to summation of theta n of tau phi n x tilde. And then we can say phi n x of x tilde. This will be simply square root of sine n pi x tilde. This is case 1. So I'm not dreaming this up. This is case 1 because the value is 0 and 0. So if you look in the table 5-2, you will simply get this as your variable. So please try to do that at home. Unfortunately, we can't do all these steps here, but hopefully you're sort of following along that this is the reason we were choosing this because the boundary conditions become simple and it makes it easy for us to choose that case. Then when you modify the governing equation, and by the way, when we say governing equation, this is the equation you are modifying. Modify governing equation, what you will get out is actually also pretty easy. What you will get out is d square theta, d theta n by d tau is equal, what you will get out is minus n pi square plus dA theta n. So you can try to see this. This is a little bit, it takes a few steps on this step, but we have done this exact thing before. Only thing we did not have was a dA added here, but when you can see that now I have an extra minus dA, so theta, this becomes a minus dA theta n, and the minus n pi squared theta n comes from the by parts, which we have discussed before for FFT. And finally, theta n of 0 in this case would become basically phi bar of x tilde comma 0, phi n of x tilde, dx tilde of 0 comma 1. And this is a very messy function, minus sinh of square root of dA into 1 minus x tilde by sinh of square root of dA sine of n pi x tilde dx of 0 to 1. Okay. I know this is a little bit pretty bad, and I also did not end up trying to even bother evaluating it. I just did this numerically, as I will show you in a second. But it's an integral of sinh multiplied with sine. So I mean, it is possible to integrate this, but it is just messy. So we will just use numerical integration. But you can technically evaluate this. And finally, if you solve and substitute, your final expression would look like something. Theta of x comma tau is theta of steady state, which is we know what the value is, plus summation of 1 to infinity theta n of 0, which is this value, exponential of minus n pi square plus dA times tau into square root of 2 sine n pi x tilde. All right, so I'll give you a couple more minutes to just write this down. I do apologize. This was a long example, but I just wanted to walk through this whole thing once with you to make sure you're seeing all the details. And then we can try to close the loop on this problem. So first, any questions here? Anything that's confusing? Anything that you would like to get clarity on? Please let me know. So basically, the whole approach here was theta steady state helped us homogenize the equations. Theta steady state was a little bit sort of complicated functions. So things like theta n 0 have a very complicated form, but you can technically solve it. And then we get this sort of summation series where we can evaluate theta n 0. We can sort of multiply with n pi square plus dA times tau into square root of n pi x. And if everything is done correctly, essentially we should get the solution that we are expecting, that the concentration profiles will go, and then for small Damn-Coulomb numbers will become linear at steady state, and for large Damn-Coulomb numbers will have this curved profile. So first, any questions, anyone, as you're all writing this down and taking notes? Please feel free to ask questions, sort of like I know it's a long problem. Yes, so I have question on chat. When we do the integrates by parts, is it always true that the derivative terms cancel and leave n pi square, or does it depend on the case? Yes, so the good question. So it will depend on the, Joe, it's a good question. It will depend on what your boundary condition is. Remember, in one of the examples we did, we had a n plus half pi. So if you have one of the derivative conditions, one of the derivative and one value conditions, then you typically have n plus half pi's because that's your lambda n. And if you have the case 1 and 4, then you have cos n pi x or sin n pi x. in which case you tend to have the n pi square. So that really depends on your lambda n value. And so lambda n value, so it's a lambda n square. Now, whether it's n pi or n plus half pi depends on the case you are at. So it's a good question, but it really depends on the case by case basis. Does it make sense? So it's a lambda n square. Let me just quickly show in to what Joe was asking. Let me see if I can pull up the. Sorry, just give me 1 second. I'll just open PowerPoint and I didn't bother to open it today. And so I'll open this here. So remember the table here. So this n pi, n plus half pi. So whatever is next to the x is your lambda n. So n for this case it was n pi because x pi is x tilde. So n pi square. This will become n plus half pi square, n plus half pi square, and then this will become n pi square again. So it's either n plus half pi or n pi typically, and that's sort of the approach that you can try to remember. And then I have another question. So in general, it will be lambda n square if your boundary conditions are homogeneous, or rather minus lambda n square. If your boundary conditions are homogeneous, those boundary terms always drop out. But if you're not able to make them homogeneous, then you have to carry out those terms and carry on through the problem, which makes it more difficult to solve it. So that's why we are going out of our way to homogenize the boundary condition, is to just to make sure that it becomes simply lambda n square times theta n minus lambda n square times theta n. Absolutely. Any other questions, anyone? Please feel free to ask again. Just want to make sure Zoom is not hindering any questions and you're getting all the questions answered. All right, so let's just simply wrap this problem up by doing this same thing we have been discussing on Python. I'll just show this to you and hopefully you can all very quickly follow this as well. So this is theta steady state. So np.sinh square root of d into 1 minus x by np square root of dA. Phi n was sin n by sin pi x. And now this theta 0, instead of trying to solve this myself, like I said, I am simply saying it's minus theta steady state into phi n dx. Because again, that was much easier instead of trying to do it numerically. Then theta, if you remember, is theta naught into n pi exponential n pi square plus damn Kohler numbers into time or into tau into phi n. So I've just literally written it exactly like you may be seeing in your notes. And I'm just summing over all the elements so that I make sure that I am getting the right number of terms. So this code is available for you to see. And so let's say start with damn Kohler number 0.01 or 0.1 maybe fine as well, but let's start with 0.01 and then let's run this code. And then I will show this to you. I'll try to animate this. It takes a few more seconds to run just because we are looping through a bit more here. So yeah, so this is essentially t equal to 0, again 1 to 0. Then we start to go further in. Is it updating or not updating? Not sure why it's not updating this value. Just give me 1 second. It's not updating. Okay, so now it is updating. It's just a lag, I think, in the. So yeah, I mean, so apologies for a little bit of lag. It's just taking some time to update this, but as you can see, we are approaching sort of this one value. And let me try to go back a little bit early. So hopefully you can see a little bit of the dynamics. I think it's probably the zoom on top of the Safari trying to just some lag. You can see some curve here. If I go 0.05, hopefully it does update. Yeah, you can see more curve here. So it's sort of going towards that from the unsteady part. And then let's say 0.01, it sort of looks even more curved like this. And then it hasn't even reached the boundary. So it does work out for damn Kohler number 0.01. And now let's do damn Kohler number 100 and run this code. And so in this case, we expect that a steady state will not even reach the last point. We will just empty all the concentrations early on. So let's say 0.16, we are here. And then let's say, let's go higher, 0.75. And basically we are at the same point, right? I can go even further high. And even at steady state, we see a curved profile and not a linear profile as expected, because at dam core 100, basically the last 50% or so of this core is practically just not used. It's just at zero concentration. So a simple sort of code can help you sort of get all the time dependent problem with a non-homogeneous boundary condition, unsteady reaction diffusion equation, and you have the full solution here. All right, so any questions, anyone, before we take a break here? Any questions? Let me just open up my windows here. Any questions? All right, so this was a sort of a longer example than I had initially anticipated. So let's do this. We'll just take one break, but make it a longer break instead of having two shorter ones. So let's come back at 9:30, and then we'll do like a 20 to 25-minute review, and then 15 to 20 minutes of Q&A. For the next 8 minutes also, I will be available if anybody wants to ask questions, but I'll not teach anything new. I'll just keep answering questions. So let's start at 9:30 sharp, and for next 40 minutes after that. But I'll be on Zoom if anybody has questions for the next 7 minutes or so. All right. So let's start at 9:30. You can stretch out, take a break, and then we'll discuss from 9:30 to 10 a.m. Okay. And I'm open to questions if anybody has in the meantime. I'll stop sharing for just so that you can ask questions if you have any. Sorry, folks. I just by chance dropped my my laptop somehow. Just stopped. All right, I'm back. So luckily, light back at 9:30 sharp. So let me share my screen. Can you all hear me all right? Um, Hi, can everyone hear me right now? Apologies for all the issues. Quick thumbs up would be great. Can folks hear me fine or not? If anybody can just maybe give a. You may have to unmute because I'm somehow having trouble
We can hear
seeing.
you.
Okay, perfect. Thank you. Thank you. Yeah. All right. So I'll not take more time. Apologies again. I'm not sure why my laptop isn't working. So I'm joining from my iPad. Let's begin and let's discuss the exam review. And basically, what I want to focus on now is really sort of focus on the key concepts that we have covered in this part, and then what do you expect? What should you expect in the exam? And basically, like really what to focus on in the exam. So I like to really divide this sort of exam review in two parts. One is sort of the key concepts, and then one is sort of the solution procedures. Okay, so solution or rather let's say problem types. Okay, so problem types. So if you want to think about concepts, what concepts we have discussed is flux. So we have discussed Fourier's law, finding flux, Fourier's law, Fick's law, Fick's law, average velocity, molar average velocity, and I'll go through them, but just to summarize that, and then we discuss flux through a surface, flux through a surface. Then we discuss governing equations, and then we discussed boundary conditions. Okay, so that was sort of the key step that we were focusing on. And then in the problem types, what we really focus on is 1D steady. We focus on approximately 1D steady, which is two parts, pseudo steady, pseudo study or 2D to 1D. Then we have the 1D unsteady problems, which are the similarity variables for semi-infinite geometry. Then we have the nonlinear problems for using the regular perturbation. And then finally the FFT for linear problems with boundary surfaces. Okay. So that's sort of the division, I would say. In general, as you might have seen from your practice exam, expect a long problem on this and this side, and this is typically where I would basically say long problem or long problems would be on sort of these sort of longer places. We'll ask you to derive and govern equation, or sorry, state the governing equation, state the boundary condition, cast it in the form of 2D unsteady, 1D unsteady, and so on. Slowly reduce it and ask you for different solution procedures. You shouldn't expect to do like a full blown calculation where you will be doing a lot of the details, but you will be expected to know steps, just to show you that you understand the processes. And this is where maybe more like short problems, how to apply different boundary conditions, how to think about sign, how to do the interfacial balance, and those kinds of things are key here. How to find flux through a surface. And so those are more like short problem types. So these are the key concepts. So hopefully if you see them together now, all of the things that we have discussed from the start makes sense. But any particular questions about sort of these structurally, like, what, like these are all the things we have discussed, but sort of we will test you sort of basically on almost everything from here, on this slide. But like I said, long problems expect more on the problem types, and then the concepts are more suited for these short problems. So any questions here? And let me see if I can manage my chat as well here. Okay, I see a chat. How does the exam compare to the practice exam? Um, so I would say practice exam, it's probably similar in sort of difficulty level. To give you an idea, last year when we did this exam, the average was around 33. So when we had set the exam, I typically think out of 50, an average of 30 to 35, the class is doing well. And so they got an average around 33. And I would definitely encourage you to look at the rubric to understand that it's not about just getting to the right answer. Even if you show us, you understand the basic concepts and so on, we will basically be able to, we will basically award you credit. So yeah, I would say it is comparable to the practice exam. It might be slightly on the long side. Again, don't worry. What I've seen it, I mean, Saradeep was able to finish it within an hour. But we just want to make sure that, because of course, the ATAs and myself, we are more conversant with this topic. So I think 90 minutes should be enough. But I would recommend for those, specifically for those of you who feel that you are slower test takers, just start with the long problem first, because that just again gives you that peace of mind. Those are also tend to be the ones that are more scoring. Again, don't waste your time, but that's just my recommendation. You can choose to also do whatever works for you, but that should be, so I would say it's comparable. And like, if you don't know a problem or two, don't worry. Averages are not super high in this course, but your final grades, trust me, would be pretty, like, it'll be on a curve, and we are generally pretty decent with like grading and so on. So I would just be relaxed during the exam and make sure you're being able to attempt everything and show us what you know. And expect the practice exam to be reasonably representative of what you will expect in the exam one. Other questions at this point? Okay, so I will keep going. So now let's start with the Fick's law and the key ideas. So concepts and the concepts. So we discussed Q is equal to minus K grad T. So this is the conductive flux. Conductive flux. We discussed about for Ni. For Ni, we have two approaches. Either we do C of Vi plus Ji, or we do a Ci V molar plus Ji molar, where V is summation of Ni by rho, whereas V molar is summation of capital Ni by C. And why this is important is that for liquid phase systems, we'd end up using the top equation typically for liquid phase. And for gas phase, we start using the bottom one. Typically gas phase with constant C. Okay, so that's when you typically start to use this one. But in general, also you can assume wherever generally you have gas phase, using the molar average velocity makes sense. For using Fick's law, applying, invoking Fick's law. This was Fourier's law. Fourier's law. Fick's law allows us to also make it easier for constant rho. The Ji becomes minus Di grad Ci, and constant and pseudo binary, and constant C, the Ja becomes minus Dab grad Ca. So this is typically what you invoke. So for the constant C problem, you invoke the bottom definition. For the constant rho problem, you invoke the top definition. So that's sort of the typical idea of using these things. So this is sort of the basic stuff we discussed on fluxes. The one last thing I want to just emphasize, please make sure you remember this, how to do this. It's very important to get your boundary conditions and just knowing how to evaluate the fluxes. This is this in your homework as well. Qn is Q dot N. And so remember, we discussed how to take N is grad F by gradient of grad F and so on. And then you can have a plus minus sign and so on. So just remember to know how to take this as well. There was a homework problem on this. There was a class problem on this. So this was also how to evaluate this, because this can also especially help in getting the signs right of sign of plus and negative sign of these. So this is a flux part of it. We have not gotten to the governing equation boundary conditions yet. So this is a flux part where really this is the main overall, that's the detail. So any questions on this part? Anyone? And I do apologize. I don't know if you still see my screen, but I have to go to Zoom to see if there are any chat comments. I don't know if you stopped seeing my iPad screen or not, but any questions? You can unmute yourself as well if you would like. Okay, no questions. Okay, perfect. So let's keep going. So this is sort of the first part of concept. This is just fluxes and how to calculate fluxes through a surface. Okay. The second part is governing equations and boundary conditions. Governing equation and boundary conditions. And boundary conditions. And here we will just keep it simple. We can remember this general equation that we have derived. Del dot F is equal to BV. So this is what we derived. And so this was the flux, total flux. It will include both convective and diffusive flux. And this was the volumetric production rate.
production rate, and rest of all the equations that we were given were basically derived from this governing equation. From here we got the continuity equation.
Ankur, there is a question on Fick's law in the
Okay,
chat. Can you
okay,
just?
yeah, thank you, Sarabhi. Can you explain the difference between constant C and constant rho for Fick's law? Yeah, for sure, Samar. Thanks. Sorry for the missing because I can't see them simultaneously right now. Yeah. So for basically for constant rho and constant C is, so remember, like I said, for liquid phase, typically you can have this assumption of constant rho and constant pseudo binary, and for the gas phase, typically this. And by the way, thanks for Samar to point this out. Is actually Ja molar rather than, that's my bad. I should have clarified this. So this is Ja molar, which is minus DAB grad C and not just DAB. So the difference is really just what I pointed out. It is both DI times grad CI, but the difference is one of them is the molar average flux based on mass average velocity, and one of them is the molar average flux based on molar average velocity. So when you have constant C, you typically want to use the V molar basis. When you have constant rho, we want to use the V basis. Now, on top of that, I will go one step further and want to say that when you have a liquid phase system, when you are trying to solve a concentration in the liquid phase, in this part of the course, you can basically assume that your velocity V bar is simply zero in a liquid phase system, because we are still not looking into bulk systems. However, when you're in a gas phase system, even though there is no bulk convection, you could have a V bar or a V molar system, or V molar to be non-zero. So that's why whenever you have a gas phase system with constant C, we typically resolve to using the V molar system because it gives us a simpler form of the Ja of M. And V molar also tends to be more easier to calculate because of constant C. So whenever you have a liquid phase system, you want to stick to the definition of constant one pseudo binary, and you can assume velocity to be zero. When you have a gas phase system, you want to use constant C and use Ja of molar to be minus dB grad Ca. Plus, you can expect that the velocity and molar velocity may not be zero. They could be zero, but they don't have to be zero in this particular part of the course. So does it answer a question, Samar? Anything else that needs clarification? Okay, so hopefully this makes sense. So now let's keep going. So this is sort of so from here we'll get continuity equation, we'll get species conservation equation, which is the CI equation, and then we'll also get the heat equation. So all of them will essentially get from the, so we will basically be able to get all of them from the from our system, and this is what we used to get the three equations. That is, and I don't have to worry too much about it. I'll focus on these two more because this is the one. These are the ones we use. Del Ci by del T is V dot del Ci equal to Di del square Ci plus Ri. Remember, this is only true for constant rho and pseudo binary. If you don't have that, we need to go back to the original equation. If not, if gas phase, then you want to use del Ci by del T plus del dot Ni. Del dot Ni is equal to Ri. Okay. So if gas phase, this is the equation you want to use, the original equation in this form directly, just changing B to Ci and F to Ni and BV to Ri. Whereas if you have a constant and pseudo binary, you can use this part of the equation, which is also pretty natural once you sort of have the liquid phase system. And then for the heat equation, we haven't done too many heat equation problems, but essentially you get del T by del T. It's very similar. Del T by del T, V dot del T is equal to alpha del square T plus HV by rho Cp, where alpha is K by rho Cp, or this is the thermal diffusivity. So it looks identical. The only difference is that you also have a HV by rho Cp, which is the production rate coming in instead of a reaction system. So those typically tends to be constant values or something very simple. And in heat conduction problems, basically, again, you can typically ignore the velocity part in this part of the course. So if you have a constant rho pseudo binary or a temperature problem, just ignore velocity. But if you have a gas phase problem, make sure you use the molar average velocity, and you can expect that the velocity is not necessarily zero. It may be zero, but it's not, doesn't have to be zero. So any questions here? I'll just open the Zoom again to make sure I'm not missing any chat. All good? Okay, so let's keep going. I'll just keep going to the next part. So this is our governing equations, and then so you should know when to use which governing equation is important, and also that this also helps you know kind of reason out systems. Then we have the boundary conditions. Boundary conditions. Okay. The boundary conditions, I'm not going to spend too much time on. B is equal to B naught and N dot F is equal to F naught. Those are just constant value and constant flux. So those should be simply easy. But the one that you really want to focus on is the interfacial balance. And so we discussed this, and now you have done some examples of this also. So hopefully this makes sense. So we find the flux going through the surface relative to the velocity of the interface times 1 dot Ni minus F minus BVI dot Ni with phase 2 plus Bs is equal to 0. This is production now, which is per unit surface area, and this is the interface velocity. Okay, and remember that Ni points from 1 to 2, always from 1 to 2. So always going to be point from 1 to 2. And so interfacial velocity, I definitely recommend making sure that you are comfortable with it. You do know how to apply it, and the sign is correct. Like, so you do understand the sign that it should go from 1 to 2, and then that's typically. I mean, students generally are able to get the terms right, but the sign are typically where they make mistakes, and then that can spill over sometimes. So just recommend practicing it. You have seen several examples in class and different problems where you have applied it. So that's what I would recommend to focus on for the boundary conditions part. But any questions on the interfacial balance concept? Anyone? You can unmute yourself or ask me if there are any questions on chat. All right, so no questions. So let me go back here. So this was our concepts. So in the concepts, hopefully there are 3 parts you have seen, or rather 4 parts. But first is the Fourier's law, Fick's law, and flux flow surface. That's sort of all part of the flux part. And then we have governing equations, and governing equations, when to use them and when not to use them. You should be clear in your mind in terms of conceptual idea, and then boundary conditions, and specifically the interfacial balance is the key boundary condition here. Okay, so this is sort of hopefully kind of gives you a sense of what concepts will test you on. And then for the now what I typically like to do for the problems is, instead of sort of going through the details of these problems, which I think you can always look back at the videos and see them, I like to kind of show you all the kinds of problems we have done, so that you can remember, oh well, this was a 1D study problem, this was a 1D study problem, and so on. So for a 1D study problem, if you remember, basically we started with something as simple as A going to B, on this surface, A going to B using Ks. And so we started with something as simple as this, but as you might remember, the first thing which probably surprised you was that even though we have a reaction at the surface, it was very surprising that the constant rho pseudo binary problem, constant rho pseudo binary, what we found was that the governing equations are equations were d square Ca by dx square is equal to 0 and d square Cb by dx square is equal to 0. And that was because there is no volumetric reaction. So you can start to see now the application of what we were discussing. When you apply them, make sure you understand that when it's a surface reaction, it becomes a part of your interfacial balance and not part of a governing equation. This was the first problem we discussed. We also discussed the problem of same problem, but now A going to be in the volumetric form with Kv here. So in that case, it became a d square Ca by dx square is equal to KVCA. And then we also solved this problem and got a cosh function and so on. I'm not discussing too much into the details, but these were the 1D study problems in the liquid phase system. Then the one gas phase system problem we did in the 1D study case was actually identical, just rotated with y is equal to 0. I believe it was y is equal to L, or maybe it was some other variable, but doesn't matter. But there was basically A going to 2B, and this was a gas phase A comma B and constant C system. So in this case, we chose the molar average velocity, and we couldn't say, we had to use our governing equation as dni by dy is equal to 0, and use molar average velocity to solve this problem. So even in the 1D study case, you can see we are seeing a sort of complexity clearly arise between liquid phase and gas phase, surface reaction versus volumetric reaction. So this is sort of, hopefully, you can see sort of all the different concepts now. When we apply, all of them are used together when we solve a problem. And so you can expect like things like, setting up a problem, the right governing equations and boundary conditions is a common thing for us to test in an exam. For instance, we may not ask you to solve the full thing, but we'll definitely expect you to be able to kind of formulate this problem in a limited time format. Any questions here? By the way, you also did this problem in your homework as well with two different approaches. Any questions? I'll just monitor the chat again.
I have a question.
Yes, please go ahead.
So when we did this in class first, and then also on our homework, we used, since A goes to 2B, MA equals 2MB. Does that just come from a conservation of mass?
Correct. Yes, absolutely. And it doesn't have to be just that, actually. You can also think if I have A plus 3B going to 2C, then I can also say MA plus 3MB going to 2MC. Same idea. So exactly right. Because of the conservation of mass, if I have moles, 1 mole of A plus 3 moles of B combining to get 2 moles of C, I should be able to multiply with their molar masses to say the kgs have to add up or the masses have to add up. That's absolutely correct.
Okay, and then so this, we only really use this when we're in the gas phase systems and using the molar quantities?
Correct. Absolutely correct, yes.
Okay, thank you.
All right. So this was sort of the 1D study case. And so that's basically where you can sort of, basically the emphasis here should be how to think about molar average velocity in a gas phase system, what governing equations to use, how to set up a problem. I wouldn't really worry about trying to solve like a second order differential equation analytically in detail for this kind of problem. But this sort of, the setup is really important in this side. Okay. The second kind of problem we did was approximately 1D study problems. Approximately 1D study problems. And here we discussed going from 2D to 1D problems, okay, and the pseudo study problems. So the key idea that I want to say, so yeah, the problems we focused on were the fin problem. This was the fin problem, was this one, and the pseudo study problem was the liquid evaporating the height of time, and this was CLL. And if you remember in your homeworks, you did this with this sort of slab problem. It was 2 slabs, K1, K2. You sort of averaged out the one of the dimensions to get the 1D equation for at the end. And the pseudo study, you also did this sort of bubble with the A gas and CB, C naught, and the bubble was shrinking over time in your homework too, right? So again, just to give you a taste, you've done a couple of problems on all of this. So what I want to sort of for you to remember really in these problems, again, our focus will not be to have you solve anything in totality, but rather how do you go from 2D to 1D. So remembering to correctly integrate, defining an average. So so T of x comma y to T bar of x. How do you do that? So how do you modify your governing equation? So modifying your governing equation is a step you can expect for you to be aware, like you did in your homework problem, or in the pseudo study problem. We may not ask you to do the full concentration profiles. We may give you the concentration profile, and then we may ask you to justify that pseudo study, velocity of interfacial is very small compared to diffusion, and justify basically your pseudo study. Justify a pseudo study approximation. So these are the kinds of things we are thinking about. And think about, like, again, like setting up the problem with governing equation boundary condition basically present throughout every problem you will do. So in these problems, you can expect that you will not get like a long problem only on a pseudo study problem or only on 2D or 1D. Those are more reserved for like FFT, similarity, and like kind of going through the whole thing. Like not similarity, again, not in similarity, not solving the problem, but like sort of setting it up correctly. But or perturbation, again, setting it up correctly and maybe solving a very simple case. But you don't expect us to like you shouldn't expect us to for you to be doing a lot of analytical math, but steps that are being used within your homework problems, or how you did it in class. So going from 2D to 1D, so averaging out, let's say, the y dimension, how did we do that? So maybe a part of a problem, long problem, could be that, or a part of a long problem could be, okay, we use pseudo study. You don't have to solve the concentration profile. They'll give you the concentration profile. Justify this using, that this is correct or something like that. So that's sort of the spirit of these problems is what I will say you would like to focus on. Any questions on the approximately 1D study problems? Oh, sorry, let me just go to Zoom to make sure. Is big M molecular weight or mass fraction? Big M is the molecular weight. To answer Summer's question. Sorry, not this. I'll open the good notes here. Any other questions? All right, so now let's keep going. We are almost there. So then final stretch, we have after this problems, we had the similarity variable. So 1D unsteady problem using similarity. So in this case, I would say the most common thing you can expect is the correct similarity variable. We are not going to have you do the full similarity transformation. That's something you can rule out. But think about the problem we had in the supplementary video of M going like this, and this is in the supplementary video. You may not have seen this. You have the problem of the temperature rising with time in the homework problem, homework 2 problem 4, or this was problem 4, I think, or the simpler one of concentration like this. You can also take examples of FFT in Python, where I kind of used a solution of similarity and superposed it. Like, how do you what's the correct variable? So both dependent. So both of what is eta and what is correct theta. So just thinking about this would be very crucial part for you. Like, how do we pose a similarity problem. You will certainly not be solving one, but how do you even pose a similarity variable? So how do you think about which surface to try, and how do you? So this is also, if you look at the practice exam, this is the kind of problem you got. There is in the practice problem, and I've seen that sort of the place where the most common confusion is among the students. So that is what I would encourage you to focus on and think about. For practice, you can just do one problem, but I wouldn't really worry about trying to do the full similarity solution of something very complex. That's something you can rule out for your exam. I don't want you to be spending time trying to be prepared for something like that. Okay, does that make sense? Any questions? Just tracking Zoom. No questions there. Okay, so then let me go back. Finally, I think you have already, I'll not talk about FFT, but I'll just talk about regular perturbation. So regular perturbation, so what to expect. I mean, this is basically where we said theta is equal to theta naught, plus epsilon theta 1, plus epsilon square theta 2, and so on. So what to expect in the exam? I would say it would be fair game to say problem like the one in class. I would say that's pretty straightforward problem, the one we did in class. Something like that is fair game for an exam. What not to expect is cylindrical coordinates or spherical coordinates or something like that. So that's not something you don't have to worry about with perturbation. Whatever we'll ask with perturbation would be something simple. If at all, the question would be relatively straightforward. You should know how to apply it. This like, unlike similarity, which I think is more involved, regular perturbation is something you can expect to be asked a little bit more detailed, because it doesn't take as much time. It's relatively easy to pose, especially like in Cartesian coordinates, and you can expect a question or two on that. And then finally, FFT, like I think we have discussed, basically you'll be asked to pose up, like solve and set up a problem, and then at the end you will probably do a basis function, but you will not be solving for a full problem setup like that. So any questions at this point? We're almost out of time. I want to make sure I address any last minute questions for anyone in a couple of minutes we have. You can unmute and ask questions if you have. Any questions? So to confirm, we can use notes, iPad, laptops. Yes, so you can use notes, iPads, laptops, whatever there is on Canvas. I have seen even students watch videos of the lectures during the exam. You can do basically whatever is available. Just make sure your laptop is charged, please. I'll hate if you don't bring anything and your laptop is not charged. That can cause headache for you. So definitely make sure your laptops are charged. Anything else that comes to anyone's mind?
I have a quick question.
Mhm.
On your notes, when we were first looking at flux,
Mhm.
that the big end, that's mass flux, right? We were looking at mass flux for like in terms of mass average velocity and molar average velocity, but the big N was mass flux, correct?
So the big N is always molar flux, but this is molar flux based on mass average velocity. So these two fluxes are the same. The difference is that in this case, I'm dividing based on the molar average velocity. This is the mass average velocity, but the units are mole per meter square second for both this one, but the small n is the mass flux, which has the units of kg per meter square second. Does it make sense?
Yeah, it does. I guess I get a little confused as to, when we talked about the sum of like molar flux being equal to 0, like knowing when it equals 0, when it doesn't, depending on which one we're using?
Mhm.
Do you I-
Yeah, so that's a
yeah.
good question. So remember always that for the sum to be 0, so that maybe something I didn't discuss here, that for the sum to be 0, it has to be the same units as that of your velocity. So some small gi would be 0 because this is as you are kind of thinking about in the right form, this is the sum of the mass diffusive fluxes based on mass average velocities, right? So it doesn't have a subscript of m. So it's the mass, so it's based on mass average velocity, and its units are also kg per meter square second. But for ji of m, this is also equal to 0 because this is the molar fluxes based also on molar average velocity. Does it make sense? So it's like both of them have to be consistent with each other. But a ji will not be equal to 0 because this is based on mass average velocity, but my units are mole average, and similarly, small gi of m will not be equal to 0 either.
That makes
Does
sense.
it make sense? Okay.
Thank you.
Other questions, anyone? I'm happy to stay a couple more minutes extra if needed. Just go into the chat. Let me see if there are any questions. No other questions. All right. I mean, hopefully, if you have any questions, you can always email me and email Sauradeep. Sauradeep will also have his office hours tomorrow from 4:30 to 6 p.m. All the best, everyone, for your exam. I will send one announcement for Canva just so that you have all the reminders for the exam. And then, let us know if you have any questions. And tomorrow, please make sure to attend Sauradeep's office hours in case you have questions and so on. All right. Perfect.